Hello and welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem astral superposition. This is the first problem from the January 2025 USACO Bronze Contest. And in this question, we are given two overlapping photos, and our goal is to find the minimum number of stars in the first photo. To make this task possible, we are told how the second photo was created. Each star in the first photo was either deleted or shifted A units to the right and B units downward. So, for example, if we have this 3 by 3 photo of stars, we could maybe say A is 1, B is 2, and you can see that photo 2 would be the same photo shifted down 2 units and shifted to the right 1 unit. And then we could also delete stars from photo 2 as well. And what we receive in the problem as an input is this combined photo. So a white pixel represents a pixel where there is no star in either photo. A gray pixel represents where there is only one star in both photos, and a black pixel represents a location where there are two stars. And we want to take this information, this combined photo, and work out what is the minimum number of possible stars in the first photo, or if there is no such possible first photo. So it could be an impossibility result as well. If it was impossible to produce this combined photo given the values of A and B, then we'd print -1 instead. And our first key observation in this problem should be that brute forcing over all possibilities for photo 1 is impossible. This would be an exponential runtime algorithm, and anytime you have an exponential runtime algorithm in USACO Bronze, it is a good idea to start looking for a greedy algorithm. So one of my favorite ways to come up with greedy algorithms is just to start with a basic idea, see if it works or not, and then try to tweak it if any problems come up. So let's start with what could be argued to be sort of the most basic greedy idea. We're going to set a counter to 0, and then we're going to loop over this combined photo. And when we loop over the photo, we're going to be searching for stars. And each time we see a star, we are going to remove that star. So for example, if we were looping over this combined photo and we saw a G here, that would represent one star. And we're going to say that that star corresponds to a star from photo 1. So we're going to remove the star at coordinates row call and add that star to a copy of photo 1. However, if there's a star at the current row and call, we can also look, is there a star shifted A units to the right and B units down that we can also remove at the same time by adding it to photo 2, right? Any star that we add to photo 2 saves us from having to add a star to photo 1, so that helps us find the minimum number of stars possible. So we're going to check the coordinates row plus B and call plus A, and if there's a star present there, again, it's not guaranteed to be present, but if there is a star present there, we will add it to photo 2. And then for this, we should increase our count of the number of stars added to photo 1 by 1. So we add 1 star to photo 1, and we potentially add 1 star to photo 2. So when you come up with a greedy algorithm like this, and this algorithm may or may not work, what you want to do is test it on small examples by hand. So you want to sort of try to falsify your algorithm and then improve it if you do find any errors. All right, let's take a look at a small example together. So here we have our combined photo. I've removed the W's and replaced them with dots to make it a little bit easier to see the stars. And A here has been set to be 1, and B is 0. So that means photo 2 is just photo 1 shifted 1 unit to the right. So let's start here by looking at the top left corner, and we immediately see a star. So we're going to remove that star from our combined photo, and we are going to add it to photo 1. And then we're going to check, is there any photo 1 unit to, or is there any star 1 unit to the right? And we can see that there is. So from our current position of the top left corner, we can see that 1 unit to the right, there's a star. So we can remove that star from the grid and add it to photo 2. So if I'm removing a star from a place where there are 2 stars represented by a B, that means it's going to get demoted to a G, and we're going to add a star to photo 2. We're going to continue looping over the combined photo, and we're going to see another G here. So there's another star here. So we're going to remove that star and add it to photo 1. And while we remove this star, we're going to look, is there any star 1 unit to the right? And we can see indeed there is. So we can remove that star and add it to photo 2. So what we can see here is these 2 stars appear in photo 2 shifted to the right. And then we're going to continue looping. So there's no star there. There's no star there. We see a star here. We're going to add it to photo 1, remove it from our combined photo, check if there's a star to the right. There is. So we're going to demote that B to a G and add it to photo 2. And then we're going to continue looping. We're going to see our final star here, add it to photo 1. And then note that there is no star to the right, so we don't add anything to photo 2. So in this case, we can see that photo 2 is simply photo 1 shifted over, where this star has been deleted. So on this example, our greedy idea seems to work fantastic. Before we get too excited, let's take a look at one more example here. So we're going to apply our greedy algorithm to this combined photo with, again, A is 1, B is 0. So we're going to take a look at the first star here, and we can see that there is a star. So we're going to add that to photo 1. And because there's a star to its right, we can add that star to photo 2. And then we're going to remove those 2 stars. Then we'll continue looping, no star here anymore, and now we get to the B in position 3 here, and we can remove a star, so that gets demoted to a single star, and we add a star to photo 1. Now there's no star to the right, so we don't add any stars to photo 2, and we would continue on. The problem here is I've left a star behind in my grid. So there's 1 star left over here. And let's see if I can add it to any of the photos. I claim I can't add it to photo 1. I can't add it to photo 1 because there's already a star in that coordinate. So I can't add it to photo 1. I also can't add it to photo 2 because in order to put a star where this question mark is, there would have to be a corresponding star 1 unit to the left in photo 1. Because there is no such star, I can't add it to photo 2. And this is problematic. So it seems like maybe I should print -1 here. However, I do have this star that I added to photo 2. And if I instead added that star to photo 1, then I would be able to add this star to photo 2. So in this case, I can actually remove this star as long as I'm willing to take 1 star from photo 2 and return it to photo 1. So this complicates my greedy algorithm because I have to sort of worry about this case of what happens if there are stars left over in the grid after I go through this algorithm. So let's take a look at what those cases are. Our goal now is to fix our earlier greedy algorithm to handle the case where a second star could be left over at the coordinates row call. And there are 2 cases. Case 1 is a star at row -B, call -A, was added to photo 2. And in this case, I can move this star to photo 1, which then allows me to add this star at the current coordinates to photo 2. Why? Well, if I add B to row minus B, and I add A to col minus A, then that precisely lands me at row col, and I can add the star to photo 2. And then, so the conclusion here is we just add 1 to our count. We increase the number of stars in photo 1 by 1. And you might protest, what happens if there's already a star at these coordinates in photo 1? And the answer to that question is if there were a star at these coordinates in photo 1, then we would not be seeing 2 stars at this current coordinate because we would have removed 1 at an earlier step. So the only way we could end up in this case of having 2 stars at the current coordinates is if we didn't remove 1 at an earlier step. So it is guaranteed to us that if this situation happens, we will be able to remove this star and add it to photo 1. However, this star may not be present in photo 2. And if there were no star at row minus B, col minus A in photo 2, then we should return -1. The task is impossible. So we found an impossibility result. There is some star that cannot be added to either photo. So this completes our greedy idea, and now we're ready to jump into the code. All right, let's dive into the code here. So we're going to start by reading in T separate test cases, and then each test case is going to call a solution function, and solution will calculate the answer. I'm also going to declare a helper function here called remove, which is going to remove stars from the sky. So if it sees a B, it will remove it and turn it into a G. And if it sees a G, it's going to remove it and turn it into a star to represent that that star had been removed, but there used to be a star there. So to write the remove function, we're going to first check are x and y in bounds. So are they within the size of the grid? And then if the sky is a G, we're going to replace this G with a star. This just represents the fact that there used to be a star here. There's not anymore. And then if there was a B, we're going to replace that with a G. So we've removed 1 star in either case. If the sky is already blank in this spot, then the remove function will do nothing. Then we can begin by reading in our input. So we're going to read in N, A, and B. We're going to initialize a count, and then we're going to read in the sky itself. So this is our combined photo. This is the N by N grid of B's, G's, and W's. And then we want to loop over the combined photo. And first we want to search for a star. So if there are no stars in the sky, so that would correspond to either a W or an asterisk in my solution, then I'm just going to continue on. Nothing interesting to do at this step. We're only interested in what happens when we find a star. However, if this did not continue, then we're in the case where there's at least 1 star present. So that means the current coordinates are either a B or a G. So we're going to call the remove function on the current coordinates, and we're going to call the remove function on the current coordinates plus B and plus A respectively. So since we're adding 1 star to photo 1, we're going to increase our overall count by 1. And then all that's left to do here is check this edge case where a second star could still be present at the coordinates row call. If this case occurs, it would occur by row call still being equal to G. So that would mean that sky row call used to be a B, 1 star got removed right here, and now a G is left over. So in this case, if row is greater than or equal to B and call is greater than or equal to A, then we can check the previous spot to see if a star was removed from that location. If a star was removed from that location, that means we can move the star from photo 2 to photo 1 and we increase our count by 1, but our hope continues, right? We don't have to return -1, so all we have to do is increase our count by 1. It's not an impossibility result. However, if row and col are small or they're large and there's not a star at this location, or there didn't used to be a star at this location, then we have to return -1. So it was impossible for us to construct the first photo given the combined photo. There's no way to add this particular star to either the first photo or the second photo. And then the final step is simply to return the count. So that completes our solution here. Thank you guys very much for watching, and I'll see you guys in the next video. Bye bye.